Hi, I'm Tim, and this is the 8th video in the series about antigravity matter. This one deals with globular clusters. This video is only an overview. If you want more detail, see the antigravity matter document that's linked to the website. Globular clusters are dense groups of stars usually found orbiting a spiral galaxy. They're much smaller than elliptical galaxies, but they can still contain millions of stars. As we've seen in previous videos, globular clusters are fragments of a preceding galaxy's dense inner core. They contain old stars from the preceding galaxy, but they lose stars and lose mass as they orbit the current galaxy. The dense inner core of the preceding galaxy has broken up unevenly because the material in it was in an AGM excluded state and behaves in ways that are reminiscent of a liquid. The structure of a globular cluster is as you might expect. The stars in the centre have got sufficiently dense that they've excluded antigravity matter from a volume of space in the middle. This volume of space is surrounded by an AGM boundary, so the stars within the AGM boundary are in the AGM excluded state. Outside the AGM boundary, there are more stars that are in the AGM mixed state, and the motion of stars in the globular cluster is chaotic, falling inwards, interacting with each other, and flying outwards again. Unlike the globules in a previous video, there's no clear surface to a globular cluster, and the antigravity matter boundary is somewhere inside the cluster. Nevertheless, we'd expect the density of the globular clusters to be strongly affected by the AGM exclusion density. This is because a globular cluster loses energy as the outer stars are affected by AGM drag. A cluster that is less dense will have more stars in the outer region and will lose energy faster. As the cluster gets denser, the rate of energy loss reduces. So here are the Milky Way's globular clusters plotted on the same graph as the globules. Now bear in mind that when you compress an object, it actually moves in this direction on the graph. So we can see that the globular clusters are significantly denser than the AGM exclusion density defined by the dotted line. However, there is a large group of clusters that is within the oval outline that appears to be parallel to the dotted line. But there are many other clusters that are spread out below the oval outline. We define a function called GC relative density, which is proportional to the cluster's displacement perpendicular from the dotted line. And now we plot the cluster's vertical distance away from the galaxy plane against GC relative density. And we find that clusters that are within 40,000 light years of the galaxy centre show a relationship. Clusters that are closer to the galaxy plane are less dense. So what's going on? The globular clusters are orbiting through the antigravity matter atmosphere. They're affected by a strong antigravity matter wind. The antigravity matter wind pushes the AGM boundary inwards at the leading face and makes the cluster denser. The globular clusters are all orbiting at approximately the same speed relative to the galaxy centre. Away from the plane of the galaxy, the antigravity matter is only moving slowly. But in the plane, the antigravity matter is orbiting with the galaxy disk. So the relative velocity of wind for most clusters away from the plane is fairly constant, but closer to the plane, the relative velocity reduces. That means the globular clusters that are away from the plane are much denser than the globular clusters that are close to the plane. So this graph is demonstrating the effect of the antigravity matter atmosphere. Okay, I haven't added any new terminology, so I'll end this video there.